Okay, good. So let me go ahead and introduce you. The student, I saw quite a few students trickled in. Okay, and so this is for students. So today, welcome to lecture 23, and we have in this particular sequence, I have gone through the training using GPUs, and also last time I talked about the levels of abstractions, and I talked about CUDNN, I talked about frameworks, and then I talk about platforms like an environment, like ML model scope. And so today we're going to have Carl Pearson, who's my senior PhD student, and he has been teaching ECE 408 and 508 with me, and then he has also been teaching various intensive courses like the POM Summer School in Barcelona every year with me. And so Carl is a world expert in GPU code optimization and benchmarking, performance measurement, and so on. So there's no better person to talk about the new NVIDIA profiling tool, Nsight. And so Carl, take over. And if you have any questions, students, just send a message, and we'll try to answer your question as we go. Okay, Carl, take over.
Yeah, great, thanks. So full disclosure, I've never done a remote lecture before, so if you asked a question and you feel like it's not getting my attention, I probably just didn't see it. So I guess unmute yourself and jump in, or maybe Professor Hu, if he's keeping an eye on it, can interrupt for me. So exactly. Yeah, like Professor Hu said, I'm getting a lot of echo actually from someone. Okay. It seems good now. So like Professor Hu said, I've done a fair amount of work on GPU performance in a variety of ways. And relatively recently, NVIDIA has switched profiling tools from sort of an older set of tools, maybe that you're familiar with, the NVIDIA Visual Profiler and NVProf, to something new that they're calling the Nsight tool suite. And two parts of this system are Nsight Compute and Nsight Systems. And so the purpose of this lecture is really to introduce both of those tools. These are the tools that are available to download on macOS, Linux, and Windows. On Windows, there's also integration with Visual Studio, and that will be substantially similar to what I'm going to describe here, though I haven't myself used it. So if you're on Windows and have used Visual Studio, then I think a lot of this will apply, though things might not be laid out in quite the same way. So these are both tools developed by NVIDIA specific to GPU performance. There's sort of system level performance profiling, which I'll actually talk about second, and kernel level profiling, which I'll talk about first. So we're not really going to talk about, there's a variety of other performance tools. gprof, perf, vtune. I mean, there's more than I could even list on this slide, probably, if I spent the whole slide filling it up. We're not going to talk about any of those. Those tend to be related to details of CPU and operating system performance, though those things are to some degree relevant to the overall system performance. Nsight Systems will expose some information like that to you as it especially relates to GPU performance. So we're really just going to talk about NVIDIA's tools. So basically what we're going to go through today is I'm going to talk a little bit about profiling in general, so how this sort of fits into the workflow. There are some steps that it's useful to take to prepare your application when you're doing performance profiling. This can help you get better results and more meaningful results. Then sort of before we really talk about profiling, I'm going to talk a little bit about some ways that you can just measure time in your CUDA applications, so your GPU applications. And then I'm going to sort of go through a matrix multiplication example as I go through the profiling and go over some of the results. So I'll just remind you a little bit about matrix multiplication. If you took 408, this should be very familiar to you. If you haven't, I think it'll be enough of a reminder that you can, or enough of an introduction that hopefully you can follow along a bit. And then we're going to talk about sort of the details of compute and systems.
Carl, we actually went through matrix multiplication in the first part of this course. So
excellent.
We're okay.
So is that also the shared memory, or is it Is this a shared
Yeah.
memory tiling
Yep.
also? Okay, great. So
Yep. Yep.
excellent. Then it'll be a quick reminder, and we'll all be on board and refreshed. So the other thing I want to point out is that everything that I talk about in this lecture is on GitHub. So that includes some Docker images with the performance tools built in, all the code for the matrix multiplication examples. If you know what Rye is, you can use Rye to run some of these things. Otherwise, if you have access to a GPU system, you can just compile and run them on that GPU system yourself. This should really work on any system. I mean, these are relatively simple examples. So as long as you can get Nsight installed, you should be able to kind of follow along if you're listening to this recording of this later or want to look at these slides. I think these slides are now posted online. So I mentioned briefly that we do some system level and some kernel level profiling. And so Nsight Compute is kernel level profiling. So this question is really, how fast is the GPU executing my kernel, and why is the kernel performing the way it does? So this has nothing to do with getting data onto the accelerator. It's just for particular kernels, how fast and how well do they utilize the system? But then there's a second kind of question we can ask, which is, I think especially relevant to an Internet of Things course, which might be, how effectively are we getting work on and off of the GPU? So I think a large part of the performance consideration in practice can be, and what often limits how much usefulness we can get out of the GPU is how quickly we can get work to the GPU and how much of the time in our application is using the GPU. And so Nsight Systems is a separate profiling tool from Nsight Compute, which doesn't really tell you anything about the kernel performance, but it does tell you about the rest of this. So how to get data on there, how much effort the CPU is spending controlling and coordinating the GPU activities. If you have certain operations that you're trying to overlap, when those operations actually occur, things like that, so that your code is sort of at an application or an end-to-end level performing the way that you think it is. And so we're going to talk about both of these. So commonly when we're developing GPU code these days, especially, we are not writing code on the system that the GPU is connected to. There's a few different reasons for that. I think in the sort of Internet of Things or embedded regime, the reason for that is that the embedded GPUs often have particular power or memory constraints that are not really appropriate for a laptop or a development system. So basically, right, we want, I don't know, I'm making numbers up, but we want a 5-watt GPU on the edge, whereas our laptop could support, a 15-watt GPU. And so the performance characteristics of the GPU on the target platform are very different from the performance characteristics of the GPU that may be attached to your laptop. And in 408, we have a sort of similar thought, but it's for an opposite reason. On a server, we might have 150 watts or 250 watts or more available to the GPU, and on our laptop, we only have 15. So it's sort of the same problem, but in reverse. And so typically what we're doing is we're sitting with our laptop, interacting with a remote system, over an SSH connection. And then if we have larger amounts of data, we use, SCP or a network file system or something like that to get data on and off of our embedded system. And so, or our target platform. And so the kinds of profiling that I'm going to talk about in this lecture is really geared towards this kind of development flow. So what we're going to think about doing is using one of these tools on the target platform as a first step, so on the right of the slide, to record performance information about the GPU execution. And then we transfer, that'll generate some recorded performance files. Then we transfer those files over to our laptop, and we analyze the results of those files on our laptop. And so then if we look at those and we make changes, we recompile the code, redeploy it to the remote platform, and reprofile. So there are ways to streamline this a little bit using the tools, but I thought for the purpose of a lecture, kind of stepping through that process might not be so relevant. This is kind of the most reliable way to work on this, or this will work on any platform that you can essentially SSH to. So I thought maybe we would focus on this one. So it's sort of a multi-step process here. We use the tool Nsight tools twice, once to record the data and once to analyze the data when we transfer it between. So before you start profiling, there's a few things that I think are worth pointing out. It seems kind of obvious that you want to profile code that is correct. But actually, this is a little deeper than it sounds on the surface. It's quite common for people to introduce some undefined behavior into their code that does not cause the kernel to crash or terminate under normal circumstances. So a common thing to do would be you accidentally have some of your threads writing outside of allocated memory, right? You forget that you need to check your thread ID against the size of your buffer or something. And if you're lucky, some of the threads that are writing outside this allocated memory, that memory is not being used for anything else by the GPU, and so those writes will go there and kind of be lost forever, but not cause any problems. When you're profiling, often this will cause the profiling to terminate with mysterious errors. The reason for that is that when you're profiling the code, the GPU requires extra memory in order to keep track of the various information that you've requested from it. And so you can accidentally trample over that information or data structures that track the state of the profiling and things like that, which can cause the profiling to error out. So when I say profile correct code that's correct, what I mean is not that your application produces the correct result, but that your code conforms to, the CUDA language standard and doesn't have any undefined behavior. In practice, this can be difficult to achieve, especially for code that is quite big. But I've found a useful tool is something that comes with CUDA. It's called CUDA memcheck. It's basically a binary that wraps up your program, and it will run your program, but at runtime, it will instrument all of the memory accesses that your program makes and report any that are accessed out of allocations that your program makes. So this can help you catch problems like this. And so if your profiling is mysteriously crashing or not complete, I would recommend running your code with this tool to see if there's any sort of misbehavior that your program is doing. This will cause a large slowdown in your code, so start small and work your way up. And it will also tell you what lines of code the errors are on, so you can fix them and then try the profiling again. If your code is correct and conformant, there's no reason that the profiling should not work. So if the profiling does not work, it's probably your fault. It's sort of like if you're working with a compiler, right? How often has the compilation been wrong as opposed to how often you've been wrong? So the second thing that we might want to think about doing is you can annotate your host code. I'll show what this looks like in the results later, but there's something called the NVIDIA tools extensions. It's a header and associated library that ships with NVIDIA. They're the CUDA toolkit. And basically you can annotate parts of your host code, and those annotations will show up in the visual timeline of your code later. So you can mark, in your own words, what particular regions of the code is doing, and have that marking appear later in the timeline when you see what the GPU is doing and what the system is, how the system is moving data. And so it's basically a stack of ranges. So you can push the start of ranges time spans onto this stack and then do something and then pop them back off. So you can create nested regions and things like that through these NVTX range push and NVTX range pop functions. So these are kind of handy for understanding when in your code logically the system is doing what it's doing. The next thing you might have to do is change how the code is compiled. Typically when we're profiling, we want to profile code that has the right performance characteristics, which means that we want to profile optimized device code. Non-optimized code, or code that has debug information in it, often has many more memory references and sometimes less efficient arithmetic or logical instructions. And that's because when you compile with debug mode on, often certain optimizations are turned off in order to preserve the meaningfulness of the debug information. So by default, NVCC will apply many of these optimizations to your code, However, depending on your compilation setup and what you've been doing, you just want to make sure that you're not accidentally generating device code, or your build system isn't accidentally generating debug code in your device code. And that's the -G flag in NVCC. So you want to get rid of that. And instead, what you want to do is add something called this line info flag. So that will basically generate an extremely limited amount of debug code, which basically correlates source file locations with generated machine code. So that later, when we're looking at the profiler and we're asking the question, you know, where did this time-consuming bit of machine code come from, we can have the answer through this line info call. It will tell us what location in our source code was responsible for generating that machine code with varying degrees of accuracy. So this line info does not affect the optimizations. It just sort of inserts a few annotations. So you want to remove the -G. You want to add -line info instead. And so just for example, basically what this is going to do, on the left, we have some GPU assembly code. On the right, we have the corresponding CUDA source code. And so this is a very common piece of source code, right? This is getting the block dimension times the block ID plus the thread ID. So sort of a global ID in the thread space. And so you can see on the left, if you've never seen PTX before, that's fine. But you can see the middle three instructions are moving this special CTA ID register, NTID register, and TID register into registers 27, 1, and 28. Those are the middle three lines. But basically, this thing I've highlighted in red is sort of a fake PTX instruction that gets inserted that says this block of code was generated from file 1, line 18, column 12. I think column 12 is the first B in block dim, something like that. So in any case, basically, it just inserts these pseudo instructions into the PTX that draws a correlation between where the PTX came from. So it's not magic. There are other compilation flags that look like they might be related to Nsight profiling, but they are not. So the profile flag, you want to skip that one. That's for a different kind of profiler. This debug flag, this is for the host code, but generally you'll want to skip this one as well. And of course, I already mentioned you want to turn off this device debug code. So that big G, you do not want to use that flag, and instead you use line info. And actually the man page for the NVIDIA compiler tells you to use line info instead of that flag, but I'm telling you to. And so the final thing that we really want to do is make sure that the system allows the NVIDIA tools to record the information that it wants. Obviously, if you are not in control of the target platform, you are not able to make this change. But basically, this Nsight systems will use various hooks to accomplish its profiling through the kernel and some other capabilities. And so you can ask the system whether or not it is able to do all the things that it wants to do with this nsys status command. And so, for example, you're hoping to see something that looks like the bottom. I'm not going to try to give any advice about how to fix any problems that come up. The documentation has some suggestions for that. But basically, if there are problems here, it doesn't mean the profiling won't work, but the profiling results may not be very good or not very accurate or have limited information in them. So if something doesn't seem quite right, this is another place where you can troubleshoot. So now we've talked a little bit about annotating the host code, changing the compilation method, making sure the system is set up for profiling. The last caveat about this is that when you run your kernel while it's being profiled, it will affect the performance of your kernel, right? There's this sort of physical principle that, observing the behavior of a system affects the system. So this is sort of that same thing writ large. So when you're thinking about reporting performance for a paper or for a class project, you don't want to record the performance. If the profiler says the kernel takes 3.5 milliseconds, the kernel may actually take 2 milliseconds when it's not being profiled. So you make sure you want to record these sort of absolute times of things, not under profiling. You just use profiling to improve the performance. So this trips people up sometimes, so I just wanted to mention it. So that's kind of how the profiling tools fit into the development model and what steps we want to take with our code before we really start profiling. So I'm not seeing any questions if I'm interpreting this correctly. So we'll just give a second here in case anyone wants to jump in, but otherwise we will move right along.
Right.
Great.
Yeah, go ahead.
Okay, so Professor Hu told me you talked about the matrix multiplication already, so we'll just do a real quick review, just so we can remember. So we're interested in the product of the A matrix and the B matrix to produce the C matrix, right? Each entry in the C matrix is a dot product of a row of A and a column of B. In this particular implementation, we're going to make A and C be column major and B is row major to help with memory coalescing. And in sort of the default implementation, we just assign one thread to every output element in the product matrix, and that thread will have to load the entire row and column from the input matrices. So each of those rows is accessed from the global memory space by every thread that needs it multiple times. And Professor Hu probably mentioned to you that, excuse me, this was a potential big performance limitation in this implementation. On the GPU, we have this fast scratchpad memory. So groups of threads can share this scratchpad memory. And so here we have the same thing, except instead of making most of our accesses from global memory, we make our accesses from shared memory in tiles. So in order to multiply this row of A times this column of B, we're going to step across each of it in sort of 3 phases, loading one tile from each of them in each of the phases. And then we take the row, the part of the row and the part of the column from that tile to start working on our accumulator of the dot product. And so in this way, all of the threads that are producing results for that tile make the repeated accesses from that fast shared memory instead of the slow global memory, hopefully improving the performance of our GPU code. And so in this case, basically in the basic, what I'm calling the basic implementation, right, we have no reuse for every time we load an entry from global memory from A or B. And in our particular implementation, we're going to produce 1,024 results per block, and we're not going to use any shared memory. In the tiled implementation, we're going to use a 32 by 32 tile to produce that 1,024 products per block, giving us some reuse of A and B, but at a trade-off of now we use some of that shared memory. So I hope that jogged your memory a bit if it's been a while since you thought about the matrix multiplication. So now we can just jump right into starting to understand how to measure performance of this CUDA code. So sort of the most common way that people do it, and maybe the way that you did it if you took 408, was you probably used the wall time on the CPU and CUDA device synchronize to measure the time of CUDA operations. So there's some example code here on the left, but the way this typically looks is, right, we'll synchronize the device so that we're sure the device isn't doing any work that we had given it previously. Then we'll record the wall time, launch the kernel, call CUDA device synchronize because we want to make sure the kernel is finished, right? The kernel launch is non-blocking. And then we'll record the wall time again and compare that with the starting wall time in order to get the duration of our kernel. So this is a great straightforward way to do things if you're looking at a single GPU with no asynchronous operations. But there's a few downsides to this approach. One is that the CUDA device synchronize itself may be relatively costly compared to the kernel performance, especially if, only really if the kernel is particularly fast. The other downside of this is that you have to synchronize the GPU with the CPU. So if you're trying to measure the performance of some kernel operation that's like in the middle of your application and your application has many asynchronous GPU things going on at once, this synchronization may sort of artificially change the execution of the program in a way that makes your measurement unrealistic. It may prevent certain GPU operations from being overlapped, which previously were overlapped, which might change the performance of your code. And the other thing is that the CPU may be doing something else in your application during the GPU execution, and so you are not really easily able to use it to measure the time at the time the GPU kernel is running. So for any of these reasons, this approach, though simple, might not be, a great one. So there's a way around this, but as a foundation to understand how to avoid this problem, if you haven't heard some of these CUDA terms, I'd like to introduce them. So there's something called a stream, which is a queue of sequential CUDA, I shouldn't say events here, I should say operations. So each operation in the stream is executed only after the prior operation in the stream finishes. And there's no implicit dependence between operations in separate streams. So if I want two kernels going on at once, I can put them in two separate streams. If you're thinking that you've never used a stream before, actually you have. If you don't specify a stream for most operations, you automatically get something called the default stream. Then there's something called an event, which basically can record the state of the stream. So you can basically stick events into streams, and at the time the stream executes that event, it will just sort of record the state that the stream is in. And I'll show why this is useful in a second. But the real point here is that generally, when we're overlapping operations on the device, we put those operations in different streams. There's particular asynchronous runtime functions that we need to use, like CUDA memcopy async. And you also want to avoid using pageable memory. So generally, this is what we're doing when we're using multiple, when we have multiple overlapped operations on the GPU. And so if we are, oh, excuse me, the formatting on this slide's not great. If we are, I can fix this and upload it after I'm done. So if we are trying to time some of these asynchronous operations in different streams, we're going to use these events that I mentioned. And so I apologize for the text in the middle, but we can just sort of focus on the code on the left. Basically, what you want to do is record one of these events into the stream before and after the operation or operations for which you want to measure the time. So that's that CUDA event record start and CUDA event record stop. And so in this case, we would be recording the time that it takes to do this memcopy followed by this kernel. So you could, record any number of things, the time that any number of things take. And then you'll need to make sure at some point on the host side, before you ask how much time passed between those events, you need to make sure the second event has happened. So sort of similar to the CUDA device synchronize, you can do CUDA event synchronize. And then there's a special CUDA runtime function that will tell you how many milliseconds elapse between the two streams as a floating point number. So instead of using the host wall time, you can have sort of the GPU be responsible for recording how much time elapsed between different events and giving you that time. And so if you have asynchronous code, this is kind of really the way you want to go for measuring the time. And so what I've done here is taken an example from that repository that I mentioned to you. So this is the basic matrix multiplication using pin memory on the host. So this is sort of a reasonable baseline. And in order to sort of estimate the performance of this, we run it 10 times. The first 5 times we consider these as warm-up runs, and the next group of 5 we actually measure the performance of. And so for a variety of reasons, it's common that the first several executions of a program will perform more slowly than sort of the steady state execution of the program. I think the reasons for this are some driver structures are initialize sort of lazily. So the first time you need to do something, it will initialize it. I think other reasons for this is that the clock speeds on the GPU are not necessarily running at maximum when the program starts, so time can take the clock up. And you can actually see this a bit here. In run 0, this time is in seconds, I believe. Oh, sorry, it's milliseconds. So it's sort of a small difference, but it's 3.75 milliseconds instead of 3.73 milliseconds. But once we run it a few times, then the time starts to stabilize. And you can see it even continues dropping down in the last 5 runs. And so all of these numbers are recorded using that sort of event record style that I mentioned before. And so as I go through the rest of these, this is the time that we're going to use to say what the performance is. And so for this code, we get 1,700 gigaflops. So this is a single precision dense matrix multiplication where the matrices are both 1,500 by 1,500 floats. So now that I've talked a little bit how to get performance measurements at a high level, we can look at how to drill down and understand why the performance of the kernel is what it is. And so the tool, like I mentioned before, the tool that we really want to use to do this is Nsight Compute. And so, sorry, this is the summary of the problem that we're looking at. So we have two 1,500 by 1,500 matrices. I picked this size because the total matrix size, each matrix is larger than the L2 cache. If you just access data out of the L2 cache instead of global memory, you get very different performance behavior than you're expecting. But the tiled matrix multiplication, in our case using shared memory, is 1.5 times as fast as the basic matrix multiplication. And so we can use Nsight Compute to help us understand this. So Nsight Compute, I mentioned this a bit before. We're going to use this to record and analyze what NVIDIA calls performance metrics. And so there's sort of 2 ways to do this. There's the GUI, which we're going to use, so there's a graphical user interface, which we're going to use to analyze the results of our profiling, and the command line interface, which we're going to use to record the profile on the target device. And so that's what this flowchart on the bottom is saying. So we record on the target platform, we download it to the client, and then we analyze on the client platform using these 2 separate interfaces. So the GPU is willing to report basically a numerical value for all of these metrics if you just use the command line interface. But consuming and interpreting those metrics can be pretty challenging. So it's useful to use the GUI to kind of help. It presents the same information, but in a much more digestible way. So there are many, many metrics available on the device. The device that I use to evaluate this is a Titan V. It's a Volta GPU, and it supports about 1,100 metrics. And so you can ask the device what metrics it has with particular options to this command line interface. And it will basically spit out a big text file, and where I've taken a bit of that text file and put it on the bottom of the slide. So you can see that unless you're really an expert in the GPU's microarchitecture, this all doesn't necessarily mean a lot to you, but it's useful to know that it's there if you're studying a particular thing about the GPU. So mechanically, to record a trace, we invoke this command line. It has some pretty useful flags. It has a variety of flags, but I've highlighted the ones that I've sort of found to be most useful. So there's a particular flag where you can tell it, this kernel ID flag, what kernel function you want, the name of the kernel function you want it to profile, and also which invocation you want it to profile. So remember when I ran that code and we executed the matrix multiplication 10 times, presumably the performance of most of those multiplications is nearly identical. So we don't need to profile all of them. We can just profile one. And so for example here, I just profiled the 6th one. This section option tells it which metrics you want to record. They're grouped into something called sections, which makes a little more sense once we look at the results. But basically, they're sort of grouped by related metrics. So a bunch of memory metrics, a bunch of compute metrics, a bunch of occupancy metrics. So we tell it that we want all of them. And then you can give it a particular output file with which to record. And then you just tell it the binary that you want it to execute in profile. So recording the trace is pretty straightforward. And so the sections thing these are some examples of the sections. So just like the metrics, you can ask it what sections it's going to profile for you with a particular command by adding the list sections flag. So in that previous slide, we just provide a regular expression that matches every single section identifier. So you can see they have something called speed of light, warp state, various memory, launch statistics, instruction statistics, compute analysis. So unless we enable them, a lot of them are disabled by default. So we just enable all of them. So once you have this profile, you can fire up Nsight Compute and import it through the menu. You can open multiple of these files at once, and you can use this particular baseline comparison feature if you want to see a comparison of two different executions in the same tab. So once you open it up, it'll look something like this. So I know these are kind of small, but if the video is not great, you can download the slides and see the images in their full resolution afterwards. But basically, you can see that there's some tabs along the top, and you can add a baseline, and then future comparisons will have multiple values, one for each different baseline. I'm actually not going to use this on the slides because it makes the application's already quite dense, as you'll see, and it makes it even more dense to look at. So I will be extracting some numbers from the application to highlight particular results for you. But I just wanted you to know that this capability exists if you end up using this. So the first section that we want to look at, or that we'll be presented with, and typically the first section you want to look at is what NVIDIA calls the speed of light, which you can use to determine what the high-level bottlenecks are. This speed of light number is basically an achieved percentage of utilization with respect to the theoretical maximum. And so depending on how close you are to any particular maximum capability of the SM or the memory, it will report that. So for example, if I was at here 58% of the floating point multiplication and accumulate throughput, it would show up as 58%. Or if I was 58% of the integer addition, it might also show up as 58% here. So this is kind of at a high level what's bottlenecking you. This alone doesn't really tell you what the performance is. But I'd say the important thing to take away from here is that there's sort of 4 different reasons that you might be limited at a high level in your application. And so I'm making up the threshold here of 60%, but typically if neither your SM, so that's the computation element, nor your memory utilization is above 60%, that means that your GPU, your kernel is latency limited. So that means that, right, in the GPU model, we try to hide the latency of different operations by having many different operations in flight at a time. And so if your utilization is low enough, basically there's not enough operations in flight to hide the latency. So we'll call this like a latency bottleneck. If your memory throughput is good, but your SM utilization is bad, you're probably memory bandwidth bound. If the opposite is true, you're probably compute bound. And if both of them are high, you're sort of compute and bandwidth bound. And typically what you want to look at there is you need to adjust your algorithm or implementation to make better use of the available memory bandwidth or to reduce your use of memory and compute in some way. So you can see that in our basic matrix multiplication, I took the screenshot for this, we're actually hovering right around 60% for both of them. So it's not immediately apparent which of these regimes we even fall into. So Typically, you will not see this result, but it's nice that we have it here because it sort of says, well, this high-level bottleneck thing doesn't really help us, so we need to drill a little deeper to understand what's going on. So right below that, you'll see some more detailed breakdown of this. In any of these tables, you can always mouse over. Sorry, I see a chat. Oh, so I have a question here. If the compute is over 60%, why is it compute bound? So I think what this question is you know, how is it that we're compute bound? Oops, sorry, skipping the wrong way. If the compute is over 60%, why does that mean we're compute bound? Doesn't mean there's 40% more compute that we can achieve. And basically in practice, once you're starting to get up above 60%, it means that you're basically never going to see 100% unless you're writing some specific micro benchmark where compute instructions can issue, you know, every cycle. So once we start getting above 60%, we're sort of at the region where every single time there's a compute instruction available, it's going to issue it. And so it's sort of similar with memory. And so it's definitely possible to achieve more than 60%, but sort of once you're getting above that region, you're basically saying, wow, we really have enough compute to keep the GPU busy. And probably if we had less compute, the program would go even faster. So I hope that sort of makes some sense there.
Yeah, Carl, I think another way of looking at it is that there's always the mismatch between, let's say, the instruction mixture that you have in the kernel versus the mixture of function units, right, that they have in the SM.
Yeah, sure.
Yeah, so unless there's a very, very, very good match, you're always going to have something less than 100%. And you know, that doesn't mean that you know, those resources that are not used are available to this kernel, right? Because the mixture does not you know, match the mixture they provided. So
sure.
So even though some of the resources are not utilized, doesn't mean that your kernel can get to them.
Yeah, good, excellent point, Professor. Okay.
Actually, we have a few more questions, Carl.
Yeah, so
this is great.
I think we had a follow-up about the meaning of compute and bandwidth in the chart. So just to make sure this is clear, if I'm saying we're compute limited, if the SM utilization is high and the memory utilization is low, right? Because that means that we're getting a little bit from memory and then trying to do a lot with it. And so that's the kind of area where we're compute limited, right? If we were memory limited, then in what we would see, how we would see that manifest is that the memory subsystem was very, very busy and the compute on the GPU would not be doing much. So that would be low compute utilization and high memory utilization. Great. Good questions, excellent questions. So like I mentioned, when we're sort of tied for memory compute and they're both 60% reasonably high, so the question is like, what's actually going on? And so if we look a little bit further into this profiler, we can see that actually the 58% of the SM utilization is actually issuing load store instructions. So the SM is busy, but it's not really busy doing multiplications or additions, it's busy issuing load store instructions. So what we can take away from this is that really we're probably memory bound because our SM is basically busy issuing a bunch of memory instructions. It's not busy doing math. So sort of in practice, we're probably more memory bound. We can see if we look down this breakdown, the first math that comes up is about only 40%. So maybe one way to think about this would be our SM is 40% busy doing math and more than 60% busy doing memory. So probably memory bandwidth bound is where we want to focus. And that's consistent with sort of what we expected to see in the global memory matrix multiplication. Right. So I just summarized the results on this particular chart. It's possible these are from 2 different runs that I had. Yeah, it looks like the numbers don't quite line up, but you know, broadly they're the same. And so we can see that in the tiled matrix multiplication, the SM utilization doesn't change, but our use of the memory subsystem goes up fairly substantially. And so we have this corresponding increase in the number of gigaflops that we get. So we can go a little deeper in here. So the next thing is the memory analysis chart. And so this is basically a diagram of what is generating memory traffic on the GPU. And so I zoomed in just part of it here, just so you could see a little better what was going on. But basically on the left-hand side, we have a green box representing the kernel. And on the right-hand side, we have the farthest away part of the memory hierarchy, the device DRAM and the system DRAM. And in between that, we have the sort of like logical memory divisions. So global memory, local memory, shared memory. We have the cache, what's called the unified cache. It's the L1 cache, the L2 and the L2 cache. And so you can see that this shows the number of instructions that reference a particular memory space. So in this case, this is the global memory one, or the global memory matrix multiplication again. So you can see that we have no local memory, no texture memory, no surface memory, no shared memory, only global memory, and we have 200 million instructions. And that corresponds to 200 million reads, basically. So right, we're spending most of our time reading, and we only write the final product matrix once. So these numbers alone kind of don't mean anything, but if we compare, well, they obviously have meaning, but we can get a breakdown of these numbers in the following section. So this is basically a table that breaks down each of these arrows into some subsections. So I'm not going to go too deep into this, but you know, what I'm want to convey here is there's a huge amount of information that's available about different kinds of memory transactions and how much we achieve. But I basically pulled some information from that table out for the tiled and basic multiplication. And so what we want to focus on really is, right, in the tiled matrix multiplication, we're replacing a large number of the global memory accesses with shared memory accesses. So in this global load cached row, so these are loads from global memory that are eligible to be cached, we reduce from 209 million to 6.6 million. And in exchange, we've increased the shared loads from 0 to 160 million. So just like we thought we were going to see, we basically replaced a large amount of the global memory accesses with shared memory accesses. One thing that I want to point out is that the L1 hit rate in the basic matrix multiplication was 95%, so it's extremely high. This is basically an answer to the question of why, well, I guess we can stay on this, why the shared memory matrix multiplication doesn't perform much, much better than the global memory matrix multiplication. When we were talking about it in the previous lecture, it's often presented as, you know, if we reduce the amount of global memory accesses by a factor of 32, we're going to get a huge performance increase. But NVIDIA has been working hard over the past few years to improve the capabilities of the caches on the GPUs. And so basically what we can see is that 95% of the global memory accesses that we make in the global memory matrix multiplication don't even get out of the L1 cache. The L1 cache is the same hardware structure that the shared memory is in. So essentially 19 out of every 20 memory accesses that we make in the non-optimized code are already happening at shared memory speed. So basically, we're getting relatively limited benefit from moving those loads into shared memory, since by and large, they were already being served by shared memory. It seems like the main effect that we get is by switching from global memory to shared memory, we actually reduce the required number of loads, roughly proportional to the performance improvement. But perhaps that's really neither here nor there. I guess the other thing that I noticed about these results that I don't have a totally good understanding of yet is that the actual amount of loads that go to the device memory end up being lower in the basic matrix multiplication than the tiled matrix multiplication. And I'm not 100% sure why that is, why that would be. But I guess one thing we could take away from this is that, you know, some of this, it's not always clear when you're profiling necessarily what is the most relevant information and what is not. I don't want to present this like profiling this will instantly answer all of your questions. It's kind of challenging and a bit of an art in its own right. But, you know, when you're seeing big jumps from 200 million to 6 million, then, you know, those are the things that are worth paying attention to. Maybe these minor variations in device memory traffic are not so important at first.
So, Carl, it may be worthwhile looking at what the change of the speed of light here, memory. So
yes,
why
right.
The jump up? Yeah.
Yeah, so the speed of light memory change, I didn't call this out, yeah, but so we've basically improved it from 63 to 85%. And this, I think this basically corresponds to when we switch this to the shared memory, we're probably more effectively using that shared memory bandwidth than we were the global memory bandwidth, even though it was cached. But I'm not 100% sure. Yeah. So this memory workload is really where we're going to see the biggest difference in this code. But I thought I'd quick. Yeah.
Well, I may be wrong on this. I actually have not a whole lot of basis, but my conjecture is that the way they define speed of light is the kind of the highest possible the memory bandwidth you can get, considering the something like the shared memory and so on. So I think what they're saying here is when you access data out of the L1 cache, combination of L1 cache and L2 cache and global memory, you're getting about 63% of the theoretical highest memory bandwidth you can get out of the among all the memory components. And then when you move the data into shared memory, because more of that is coming from shared memory, rather than L2 cache and so on, so you're probably getting higher percentage of the theoretical memory access bandwidth you can potentially get out of the chip. That would be my guess.
Yeah, I think that's almost certainly right. So I notice I'm starting to come up on the end of my time here, and I wanted to talk about the Nsight systems a little bit, but really quickly.
By the way, Carl.
Yeah.
Carl, do not rush through it. On Thursday, I was going to talk about a few higher level tools like XSP and so on. But okay. I think this is more important. This is higher priority because these are the sort of the bread and butter tools that everyone will be using, right? The XSP excellent. And so on are a little bit more advanced and they're farther away from popular use. So, let's make sure that students get really, really good understanding of this tool. So we can even come back and finish up some of the material on Thursday if necessary. Okay.
Yeah, then what I'd like to do, if that's possible, is we'll just talk about compute today, and we'll talk about Nsight systems on Thursday. The systems part of this is not as long as the compute part of this.
It's actually better. It's great because okay. XSP focus a lot on the system side.
Oh,
so
perfect.
That will be a great lead into that. Okay.
Okay,
yeah.
Great. Then I think we're great. Okay. So then we'll finish off the rest of our time by just talking about some of the other kinds of information that the profiler provides you. To really understand this, you need to understand a fair amount about the GPU architecture, which we don't really have time to introduce in the lecture. But suffice it to say that the way the GPU execution works is that the thread blocks are assigned to SMs, of which there are many on the GPU. And within those thread blocks, the unit of execution, sort of one of the smallest units of execution is called a warp, which is a group of 32 threads. And so the Nsight compute will also tell you for what reason warps were and were not executing during the course of your program, right? So we have many, many warps going, so it's not so useful to follow the life of a single warp through the kernel, but it is useful to understand why the warps were able to and were not able to execute. And so for any particular GPU, there's something called the device limit. And so this is a relatively old graphic showing Fermi and Kepler, right? We're several generations past that for now, but the principle is the same. The numbers are just sometimes different. There's a certain number of warps that each SM can keep track of. So even if every warp did nothing and used no resources, there's hardware structures that can only have a certain number of active warps. So I think on our GPU, it's also 64. So that's the device limit. So no matter what, the scheduler can't have more than 64 warps per SM sort of ready to go. Then depending on how many resources the warps use, you may be able to have fewer than that. So for example, if all of your warps use a lot of shared memory, then you can't have quite as many warps as the possible device could keep track of. So then, maybe I should skip forward here. So then that's the theoretical occupancy. So then the active number of warps is how many warps the SM actually got. And so why the SM wouldn't get the theoretical number over the entire course of the execution is, for example, if you, when you created your GPU kernel, you didn't create enough warps, so there's not even enough warps to give to all of the SMs. Or if, for example, there's some imbalance in how long each warp takes to execute. So for example, 90% of the warps in your code have finished and 10% are taking a long time and still executing, that will really bring down the sort of overall average number of active warps. Then between all those active warps, out of all the active warps, the warps can either be eligible to execute or not eligible to execute. So that is eligible and stalled. So a warp is stalled if,
Carl?
Yeah.
Carl, it may be helpful to know that these warps are actually retired kind of in order.
Okay.
So if the long-running warps are the oldest ones, then they will kind of block the new warps from coming in. I think that's the fundamental reason why, if you have some very uneven warp running times, you can have fairly significant reduction in your real occupancy.
Yeah, so I was even thinking about it a little more on the back end, like if all of my warps are done, but I still have some that are hanging out. But so this, I think, gets maybe, is a good way to highlight the point that to really understand some of these in fine detail, why the numbers are what they are, you really need to have a deep understanding of the architecture. But yes, so stalled warps are waiting for, maybe a data dependency from a previous instruction. Eligible warps have all their dependencies and are ready to go. And then out of the pool of eligible warps on any given cycle, the SM will schedule particular warps. So there's so many possible warps, and the number of warps that we actually execute is far, far lower than that. So compute will tell you this. So these bars, I know they're probably a little small for you, but basically we have theoretical, active, eligible, and issued. And so on the right-hand side, I'm basically just going over those definitions I just gave you. But one thing that I want to point out is that the eligible warps per scheduler, you would typically expect to see the active warps to be very high. The eligible warps can be much lower than that. And then the issued warps is often even much lower than that. And the reason that issued is so low is because typically only a maximum of 1 or 2 warps can be executed per cycle. And the x-axis here goes all the way out to 16. So just because the issued warp per scheduler is 1/2, that's actually not, 1/32 of the maximum. It's actually half of the maximum. So I guess I want to, we just really need to understand what we're looking at here. But, basically what this is saying is that there's, almost 16 warps sitting around in the SM but only about 4 of those on average are ready to go every cycle. So the question that you might ask is, what are the other 12 doing most of their time? And because if we understand that, we can maybe fix that, make more of them eligible to be scheduled, and then improve how fast our code executes. So I pulled these numbers out for both our products again, and we can see that actually they're substantially similar here. We have about 2 to 3 cycles on average between when warps are ready to execute. So
Carl?
Yeah.
Carl, it was actually a little bit surprising to me that the eligible warps in the basic is actually a little bit more than the tile. Is it because the tile one uses shared memory and reduces occupancy?
No, so the occupancy of these is actually the same. I think this is because, I think I was going to possibly get to this, but I think this is because, I'm not 100% sure, but I think the tiled warps spend most of their time sitting, there's not, other than waiting for specific loads from shared memory. Oh, I see, we have a question here too. Yeah, so in both these cases, so we have another question that's related. In both these codes, basically what we end up waiting on is the memory, whether it's from global memory or shared memory. It seems like, well, we can jump ahead actually a little bit here. Wen-Mei, let's actually look at that in 2 slides. So one thing I want to point out here is we probably heard about control divergence. And so this is another number that you can pull from these warp state statistics. So we'll return to the question in a second. But basically on this, for this warp state, on the right-hand side, it'll tell you the active number of threads per warp and the active not predicated threads per warp. The first number will typically be close to 32, but the second number will sort of tell you what the average control divergence is. So if a warp is, when a warp is executing, half the threads are masked off because of control divergence on average, then this number would be 16 instead of 32. So let me jump ahead and talk about some of the warp state statistics, and then maybe we can return to why they aren't ready to issue. So this breaks down those numbers that say why a warp is not eligible to be issued. This breaks down the reasons why that is. So this is for the basic matrix multiplication. And so there's a variety of reasons that the warps can be stalled. I'm not going to go through them all now. There's a link at the end of these slides where you can click through and try to get some understanding of that. But the top bar here is basically the pipeline for load and store instructions to global memory, this so-called LG, so this global, is full. And so the instruction can't issue because the GPU can only have so many memory instructions in flight at once. And so this is relatively, this is kind of what we expect. Basically, most of the work in the dense matrix multiplication is going out to memory. So we basically generate too many memory instructions here. So we can't, so the warps, most of the time when the warps are not eligible to execute is because they're waiting to issue a memory instruction, but the GPU can't sustain any more memory instructions simultaneously. So to return to Wen-Mei's question, I pulled out some of the relevant stall reasons for these two. And the first thing I want to point out is that there's sort of an average number of cycles that elapse between consecutive instructions in a warp. Right, a warp will execute some instruction and then it will be a while before the scheduler is able to circle back to that warp and that warp is ready to execute another instruction. And so for the basic matrix multiplication, it's 30. And for the tiled matrix multiplication, it's nearly 50. And so the reasons for this aren't entirely clear to me. But one difference one big difference is basically that we replace all of the global memory load store stalls in the basic matrix multiplication with so-called MIO stalls, which is the queue that the shared memory instructions go in. But we can see that in the tiled matrix multiplication, those warps spend about twice as long waiting for shared memory on average than the basic matrix multiplication spend waiting for global memory. And I'm just wondering, this might possibly be, I'm not really sure why this is. I was thinking that it's possible that once the warps are able to, no, I'm not really confident about why this would be. So I guess I don't really have a great answer for Professor Hu's question at this point. But I mean, this is
me either.
yeah.
So in fact, this is something that I could go and ask a couple of the NVIDIA architects and then see if we can all learn something. So maybe they were willing to address. So I'll try to follow up.
Maybe I can look at it a little bit before next time also. We have another comment. Yeah, so someone observed that there is a change because in our tiled matrix multiplication, we have thread synchronizations. So that actually shows up in a different row of this chart. So that's this stall barrier. So right, we have no synchronizations in the basic matrix multiplication, but most of the time in the tiled matrix multiplication, we're really still not waiting for stalls. That's only 5 of these 47 cycles on average is waiting for stalls. Most of it's really spent waiting in this shared memory queue. It could possibly be that the shared memory queue is smaller than the global memory queue. And so even if the shared memory things are being served faster, they'll spend more time waiting to get into that queue. It could just be something as simple as that, possibly.
I think so, because the overall execution time is compressed.
Yeah.
So these threads are hitting the shared memory queue faster than the global memory. That is entirely possible.
Yeah, so it's probably something like that, but maybe we can determine definitively before Thursday. So now we're really coming up against the end here. There's something really important that I do want to get to. So I think, well, we can probably do this. We can pick it up on Thursday if we don't get to it. So I talked a little bit about occupancy at the beginning. This is really only a problem typically if you're latency limited, you don't have enough occupancy, but this section can tell you what about your code is limiting the theoretical and achieved occupancy. So occupancy is basically the true amount of active warps compared to the theoretical amount of active warps. And so basically every resource that a thread block consumes will reduce the number of thread blocks that can run. So on your device, there's some number of thread blocks that can be running. If they use too many registers, that number will go down. If they use too much shared memory, that number will go down. And so the right-hand side of this says, if it were registers alone, how many blocks could run? And here it's 2. If it was shared memory alone, how many blocks could run? Since this code used no shared memory, it's maximum of 32. So you can kind of figure out how you can trade off registers, shared memory, and warps to improve your occupancy. And it will even provide you a chart that says, if I reduce the number of registers or change the block size, how much would my theoretical occupancy change? So that's what's going on here. This is sort of a detail. Let's see. So one thing that can affect the occupancy that's kind of surprising, but can happen if you don't have a lot of thread blocks to launch, is if you can sort of think of the thread blocks as executing in waves. So if, for example, we have a GPU with 4 SMs, and we have 8 thread blocks to launch on it, we could think of this sort of executing in 2 waves. But if we only had 5 thread blocks in our kernel, we would have 1 full wave and 1 wave that's nearly empty. And so it will make the achieved occupancy of this right-hand program seem to be, 5/8 instead of 100%. So even if all of your thread blocks are doing the right thing, if your kernel is small, you can have low achieved occupancy just because your problem is too small. So this is particularly problematic if you're profiling a small problem, because profiling a big problem takes too long. So you want to find the happy medium between a small enough problem that you can get a profiling done in time and a big enough problem that it's realistically consuming the GPU resources.
Carl, I think it's a little bit more nuanced than that. If you go back to that slide. So in this case, if there's only 5 blocks, the occupancy can actually be really high because we're talking about quantization effect here. And there is a period of time where only for 5 blocks, there's only one executing. So, so you will see some strange effects when the blocks have perfect number of blocks have the perfect multiples of the resources. Then the occupancy goes up, and then when you have more blocks, it could go down, right?
Yes,
because of this quantization.
Exactly. But you can imagine if I had 1,024 blocks versus 1,025 blocks, effectively, because of this effect, the occupancy would really be the same, right?
Yeah, because it's negligible. Yeah.
Right, exactly. It would be negligible difference. Yeah. So this is kind of the most relevant for small problems, but it definitely does come up. So I guess what I want to point out here is that when you're computing how much your achieved occupancy, one of the things that can often limit your occupancy is how many registers your threads use. But unfortunately, the profiler lies to you a little bit about how many registers each of your thread uses. So in these cases, it says our threads always use 32 registers. And if we have 1,024 threads in a block, then our block uses 32K registers. But actually, it's more than that. The thread will use 2 additional registers for the program counter. So it says it's using 32 registers, it's actually using 34 registers. So it's something just to keep in mind. I want to give this a little bit of time. This is sort of the final nifty thing that the compute system, the Nsight compute can do, but I think we're at the end of our time for the lecture. So maybe I could start here on Thursday. This is where you can really drill in and look at instructions are executing and how long the program is spending on various instructions. But I think
this is this will be a good place to start on Thursday. Yeah.
Okay. Well, okay. So thank you.
Good. But thank you, Carl. Again, as students, as you can see, Carl, is one of the top experts in the measuring performance and benchmarking and so on of GPUs. So that's why I wanted to make sure that we have we have the material presented by someone who actually uses it on a regular basis. And Nsight is a new program. It's a new profiling tool, and there's relatively few people in the field that are familiar with it. So we're really lucky to that Carl is on campus here. So on Thursday we're going to talk about finish the Nsight, and then I will go into a small number of topics and about higher level profiling. How do we measure the entire application across system components, because there are other components other than GPUs in the system, and also hopefully a little bit introduction to other types of the inference devices, such as the tensor, the tensor cores and the tensor, the tensor units, TPUs. Okay, so see you on Thursday.